In the previous lecture, we introduced multiple linear regression and briefly addressed some of the features that it could have and the ways in which it could be applied. In this lecture, we're going to go a little bit deeper into several of the main topics in multiple linear regression that make it so versatile and useful. We'll close out with a discussion of some alternate regression procedures that build further on multiple regression, but that we won't have time to cover fully in this course. So the three main things that we're going to talk about are polynomial models, which are fantastic for fitting high feature data, interaction models, which are amazing for determining the ways in which independent variables affect how other independent variables have their relationship with the outcome, and qualitative predictors, which is kind of the final element or component that's needed in order to demonstrate just how versatile multiple linear regression is. Again, we'll hit some additional topics at the very end, talking about things such as added variable plots and then alternative regression procedures. So for polynomial models, we can include second, third, fourth, etc. order terms in the model. So we can drop in as complex of polynomial terms as we want, and that allows our model to be, I'm going to use the term more wiggly, but have a lot more curvature so that it can better fit the data. If we have more than one predictor, we can include interaction terms with these, but typically if we're fitting high degree polynomial models, we tend to just do that when we've got one predictor in there. Polynomial models are really useful for prediction, but when we try to go to interpret the different betas or parameter estimates, it becomes much more difficult. So we tend to use the polynomial models to predict and account for variation. We tend not to look at interpretation other than is the parameter significant and or is it not, to determine if we actually need some of the higher order terms in the model. So using higher order terms, we have to be a little bit cautious about it, and it's because we can easily do something that's called overfitting our data, and we'll discuss that in a little bit. But when we use more than like a second or a third order term, especially when it's not justified by theory, we want to make sure that we're being a little bit cautious. So one of the other reasons actually that we want to be cautious is this idea of extrapolation. So we'll discuss overfitting, but extrapolation is a huge limitation of polynomial models. So especially polynomial models that have higher order terms can have, they really don't do extrapolation very well. Now there's some things like spline curves that we can do to help them extrapolate a little bit better, but honestly, if we're using high order polynomial models to fit a high feature data set, we do not feel comfortable extrapolating beyond the joint range of the independent variables. So recall how in the previous lecture we discussed what the scope of the model is. We discussed how the joint range of the independent variables creates a scope that's different than the univariate range, so we have to do this multivariate joint distribution to determine that. This is very important in polynomial models. However, in polynomial models, when we only have a single independent variable, the graphs actually become a little bit easier because we can display them in our traditional graph. So let's look at a quick example of polynomial extrapolation, and I'll be able to explain this. So I've got my graph data here. Now this could be a quadratic maybe, but things kind of flatten out at this curve, especially on the right hand side here. So when I end up fitting a curve, it ends up looking like a quartic to the fourth level polynomial works well for fitting this particular data. So nothing looks particularly untoward. Things don't look bizarre. You know, I look at extrapolating here. It doesn't look like this prediction just outside of the range of my data would be too bad. So nothing looks too weird here. But what I'm going to end up doing is I'm going to pretend that I'm extrapolating. So this goes from about -7 to +7. I'm going to predict just a couple numbers out. I'm going to go just to 10 here. So I'm going to see what would happen if I take the curve that I fit, and again, it looked very reasonable for my data, and then fit it to just a couple numbers out to this number 10. So just between us, I will already know that the actual value for this 10 is right about here. It's a little higher, I guess, than the 5, so it kind of does come back up a little bit. But what I want to do is I want to take this model that I fit that looked really good on my data and see where it falls at 10. And if I look at this model, what you see is though it looks really good for the scope of my data, it shoots up at the very end, and my error term is immense. I have an immense error for this prediction. So recall this is the actual value. Looks like around maybe 1,000 or something. The predicted value looks like it's up in like the 4,000 or 5,000 range, something absolutely ridiculous in the context of this interpretation, and the error of such a prediction would be astounding. So I want you to consider just how small or how close this predicted value is. My data go from -7 to +7. It feels like predicting something at 10 is really not that far away, and in many cases, especially in a linear regression, it might be a little far, but probably somewhat reasonable. However, when we're dealing with polynomial models, especially higher order polynomial models, even being just a bit outside of the scope of the model is very, very problematic in terms of prediction, and we really don't want to predict data that's outside the scope. Now, I want to be careful because sometimes students get confused about the scope of the model. The scope of the model doesn't mean that we have to have an exact x value at that point. So maybe I don't have any of these. I have values that are close to 0, but none of these are exactly at x equals 0. That doesn't mean that I can't use the model to fit a point at x equals 0, even if it's not in the data set. That would actually fit very well. It looks like my prediction would be well within a reasonable range of what the observed data would support. What we say with extrapolation outside the scope of the model is if it goes outside of the range of my x values, or as we discussed in the previous video, the joint range of the x values, that's where we get concerned. Another thing that I want to quickly point out here is, again, I've added in this particular case 4 independent variables, x to the first power, x to the second power, x to the third power, and x to the fourth power, but I can graph them all on the same plot because they all relate to a single x value. So when I'm using higher order polynomials, I can actually graph them without having to worry about the hyperplanes that we discussed in the previous video when I'm adding variables, because they're all transformations on the same variable. Now recall that one of our assumptions when we had multiple independent variables was multicollinearity, and that's a very, very big concern when we use polynomial models. And it's because the variable x and x squared are going to be extraordinarily highly correlated. Now this intercorrelation between these values can be reduced by centering, and all I mean by centering is subtracting the mean from each one of the numbers. So instead of using x, we'll use this little x, which is just x minus its mean. So we'll take all the x values minus the mean, and that's the x values we'll use. And we're going to use these not just for all of our x's, but in x squared, we'll take the square root of this x minus the centered variable, and in a cubic term, we'll take the cubic term of the centered variable, and so on and so forth. Now, when we center variables, this actually doesn't change the quality of our prediction, though it is important to remember that the model is now fit with the centered variable. So what you don't want to do is plug in your old x value without realizing that it's the centered variable. So if we're trying to plug in an x value for prediction, we'd have to plug in an x value on the new scale of the centered variable, not on the old scale of our uncentered variable, to make sure that we're predicting accurately with the values. Now in R, we can use the I function to add in squared terms into our model. So I'd have x plus I parentheses x to the second close parentheses plus, then I could do the third to the third to the fourth to the fifth, as many as I wanted to add in the terms that I'd like to have. And these higher order terms create new predictor variables. So each of these higher order terms are going to have their own betas in the model. They're going to have their own statistical significance tests. And again, we don't tend to interpret those betas because the interpretation is complex. We do sometimes interpret the statistical test to determine if we need that high of a degree of polynomial. So typically we start at the top, the highest degree polynomial, and then back down and see are there any that we can remove. Though recall from the previous video, we want to keep them all in up to the top degree polynomial that is significant. So again, regression is done as usual, and in fact, if we were creating this by hand, we would simply treat x squared and x to the third and x to the fourth, etc., as their own predictors, and drop them into the design matrix and do our calculations normally. Nothing actually changes in terms of calculating our parameter estimates. Now, when we don't center the variables, and sometimes even when we do center the variables, we still have multicollinearity issues. One way that we can get around this and not have to worry about having to center x every time is instead of centering x and then using that centered x variable to do all the calculations in our model, in the model, what we can simply do instead of writing y squiggle x plus ix2 plus ix3 and so on is just write y squiggle poly x comma d, where d is going to be a number that we place in. So if I wanted a second degree polynomial, d would be 2. If I wanted a third degree polynomial, d would be 3. This saves us a lot of time in our coding if we want to do high dimensional polynomials, or even if we wanted to just do a couple polynomials. It's really handy because it automatically centers the variables for us and actually does another procedure that we're not going to discuss, but makes the polynomials orthogonal, which you can look up some of the details in the documentation, which helps to address this multicollinearity issue. So this is handy. This is how I tend to drop polynomials into a model if I'm interested. So you give it the independent variable that you want to make the polynomial for, and then the degree of polynomial you want to include, and it automatically includes all of the lower terms, which it absolutely should. So again, I've mentioned this before, but we really want to make sure that we're including all of the lower order terms, even if they aren't statistically significant. So when we're interpreting significance, I mentioned we start at the highest order term and drop back down. We can remove if the highest order term is non-significant, we can remove it and then move down. But if the higher order term is significant, then we have to stop looking at it. And we say, okay, the highest order term is significant. Even if lower order terms are not significant, they still need to stay in the model. So we start with our highest order term and determine if it's significant or not. If it's significant, we stop looking. If it's not significant, we can drop down and look at the next highest order term and see if that's significant, and remove all the ones that are non-significant all the way down until we get a significant one. This said, all other things being equal, we really do prefer simpler models to more complex models, and this has to do with some an idea. It's not just about statistics, called Occam's razor, which is the simplest explanation is usually the most correct one. So if we have a simpler model that's doing pretty close to as good as a very complex model, let's say I have a linear model, just a single line, so linear relationship, and then I have like an 8th degree polynomial, and these are performing about the same as each other, then all things being equal, or all things being close to being equal, I'd prefer the linear model because it's a lot easier to understand. So in general, we prefer simpler models to more complex models unless we have a really good reason not to, and that's where our statistical significance can help us. Same thing with r squared, so the amount of variability. We can look and see, okay, r squared's bigger or r squared's smaller. Or recall we talked about how r squared always goes up when we add terms in the model, so maybe the adjusted r squared's bigger, the adjusted r squared's smaller. The other thing we can do is look at the degree or the size. So we could say r squared is statistically significantly bigger, but maybe a better question would be to say, well, is the size of the growth meaningful to me in my application? Because maybe that linear relationship explains 73% of the variance, and maybe the 8th degree polynomial explains 74% of the variance. But perhaps it's the case that even if that change is statistically significant, 73 and 74% are really close, and because of that, I might just stay with the linear model. So we really do prefer the simplest models that we can have, unless we have a really good reason not not to do that. Now, there are some drawbacks to polynomial models. So the multicollinearity issue is an issue, and even in spite of centering, it can still be something that comes up. Polynomial models use additional degrees of freedom, which can give you higher standard errors depending on how much error is accounted for in the new terms. So if you just drop in a whole bunch of polynomials, that can be a problem. The coefficients really can't be interpreted. So even the linear coefficients, you cannot interpret the linear coefficients in a high order polynomial, even if you could before. Even the intercept kind of has a meaning, but even that, I mean, even that is difficult. The extrapolation, very, very, very limited, certainly when compared to regular old regression. And then we can easily overfit our data, leading to really poor prediction of new data. So the concept of overfitting is when we have some random noise that our model is so complex that it captures a lot of the information that's contained in random noise, but misses out on the real underlying relationship. So let's look at an example real quick. Here's my data, and I'll just go on and tell you I made this data. This data has a line underneath it. So what I'm going to do is I'm just going to say this data is kind of random noise around a linear relationship. And I'm going to fit two models to this data to illustrate overfitting. Now, this line comes pretty close to most of the data points and does a really good job at describing kind of the underlying relationship of what's going on here. So if I dropped in a new data point, given that my underlying relationship actually is linear because I made up this data, then the new data point would actually kind of fall right around where this line is. Now, I could also fit, this is a 1, 2, 3, 4, 5, 6, 7, 8 data points. I could fit a 7th degree polynomial and get perfect fit on all of my data. So this is my 7th degree polynomial. It perfectly fits all of my data. Look, zero error. The line goes through every single one of these data points. And the problem is that the real relationship that's kind of underneath this data, and again, it's kind of this line that I know, is actually much farther away on average from the super curvy line than it was from my straight line. Now, the straight line doesn't perfectly catch the underlying relationship between x and y in this case, but the super curvy line is way, way, way off. Now, the trick is, okay, well, how did you know, like with a new data set, whether you should have a really, really curvy line or a straight line? That is, how do you know, given that with real data I never know what the underlying relationship is, which I should use? Should I use a straighter line, a lower dimensional polynomial, or should I use a super curvy line, a higher dimensional polynomial, and how should I find out? That is a great question. There are a bunch of different techniques that we can use, and many of them are covered in our machine learning course. So I encourage you, if you're interested in some of the techniques, to find that out. The short answer is a technique called cross-validation, which allows us a way of looking at our data that gives us a good idea of which of these is closer to what's truly going on in the underlying relationship. It's a very, very cool technique. All right, so interaction models. And again, we've talked about these before, but interactions are the product of predictor variables that are incorporated in the model. We just drop in the product of predictor variables. Interaction, the core definition or meaning or idea of interaction is that the relationship of one independent variable with a dependent variable depends on the value of other independent variables in the model. So let's say that my relationship is very positive between one independent variable and the dependent variable. If a third variable was positive, but that relationship is negative if the third variable is negative. So that I can't just make claims about the relationship between my independent variable and dependent variable. I need to make those claims conditioned on what the value of the other independent variable is. So the model for a two independent variable situation is just as so. The interaction term is this beta 3, where we literally do multiply the two independent variables together. One interesting thing about this is that we can rewrite this in terms of x1 or x2. So notice that the coefficient of x1, if I just rewrite this term algebraically and factor out an x1, the coefficient of x1 depends on x2. And if I reorganize this in terms of x2, the coefficient of x2 depends on x1. So this is what we're saying, is that the relationship between x1 and y, that relationship, which is x1's coefficient, is not just a constant number, it's a number that depends on the value of x2. So the relationship between x1 and y depends on x2. Now, mathematically, that's identically the same as saying the relationship between x2 and y also depends on x1. So these are both happening together. Note that beta 3 is involved with both, but the constant that they have is different for each one of these. So this beta 3 term is involved with both of these relationships, and it makes the interaction term kind of difficult. We tend to like to interpret it one way or another way, but actually both of these are true at the same time. So we can't really tell which one's affecting which other one without some additional information. Now, interactions are difficult to interpret, renownedly so. Partially because of what I was mentioning earlier, but partially because if we start adding more and more variables, it becomes variable 1 impacts variable 2's impact on variable 3's impact on variable 4's impact on variable 5's impact of the relationship between variable 6 and the dependent variable. And at that point, it really does get quite silly and frankly impossible to interpret. So typically, anything that involves the interaction of 3 variables or more is very commonly listed as not interpretable. Doesn't mean it's unimportant, it just means that many people don't try to interpret those. So again, as we mentioned, this implies that the relationship between an independent variable and dependent variable is affected by a third independent variable. But though this is true, we can't say, hey, IV1 impacts the relationship between IV2 and the dependent variable, nor could we say, hey, IV2 impacts the relationship between IV1 and the dependent variable. We can't say this is the one that does it or that's the one that does it without additional information. It's not to say we can't design studies that can claim this. It's to say that that isn't a default claim, certainly not with the observational data that we often deal with in regression. This said, and this is a bit of an admission, but very often we do this anyway. So we can't really make this claim, but very often we phrase it in a single direction. Sometimes we phrase it in both ways, and I guess you could argue that that's best practice, but honestly, we usually just use one that seems to make sense. And honestly, typically, when we're doing this, one of the directions seems to make more sense than the other direction. Typically, one other thing that you'll look at is that sometimes if you're working with a researcher, researchers are interested in the relationship between one particular independent variable and the outcome, and then want to account for this second independent variable. So when you have a situation like that, well, then I'm looking at the relationship between that one independent variable they care about and the outcome, and seeing how that other one that they just kind of tossed in affects the relationship of interest. So sometimes that happens too, in which case you can just phrase it in the direction where it's of interest. We do need to be kind of careful, though, with our language to make sure that we're not implying that we have some reason to believe that this is the only way it could go. So again, absent other information, we don't really know which direction is necessarily correct because they're both kind of true. All right, so with interactions, the interpretations of main effects are a little bit different. The interpretations of the main effects actually happen at the zero of the other independent variable. So let's say I have, I don't know, age and weight as two independent variables, and I'm interpreting the coefficient of age. Well, that interpretation happens at the weight of the other independent, at the zero of the other independent variables. So the interpretation of age would be for when weight equals 0. which sometimes isn't what you mean, and in fact, very often that's not what you mean. This is kind of a big problem and something that many students kind of forget about, but is really, really important. So note that this interpretation change happens even if the other variable isn't statistically significant. So it doesn't have anything to do with the statistical significance of the variable. It's actually the addition of the interaction term that forces this to be true. So previously this didn't matter, we just kind of accounted for the other variable, but because when we have an interaction term, it changes the interpretation of the independent variable. It's really, really, really important to center all of your continuous independent variables so that they are interpreted at the average. So that is, when I'm interpreting age, I'm interpreting the coefficient of age not when weight equals 0, which is a nonsensical claim, but I'm interpreting the coefficient of age when weight is at the average age, which is a much, much more reasonable claim. All right, so interaction models can have three main types. One we'll call an additive effects model, which is that there's no interaction at all. One we can call a reinforcing effects model, which is that as the values get bigger, then the effects get bigger, they build on each other. And one which we can call an interference effect, which is that as the second independent variable gets larger, the relationship between the first independent variable and the outcome gets smaller. So in an additive effects model, you can see that it doesn't really matter what the value of x2 is, whether it's 0 or 1. The relationship between x1 and y is still the same. That is as x1 goes up by 2, y seems to go up by 1. So the nature of this relationship is constant. For reinforcing effects, we start out with this relationship between x1 and y when x2 is 0, but then as x2 increases, the relationship between x1 and y gets more positive. So it reinforces, x2's increase reinforces the relationship between x1 and y. And then for the interference effect, we start out with this relationship between x1 and y, but then as x2 increases, note that this is x2 equals 0, this negative sloped line is x2 equals 1. So as x2 increases, the relationship between x1 and y is found to be decreasing. And in fact, it's interesting to note, especially in this case, that below x1 equals 2, it actually changes which is better, x2 equals 0 or x2 equals 1. We see that x2 equals 1 is better, has a higher y value, I should say, when x1 is 0, and x2 equals 0 is worse. But then as x1 grows it positively, let's say x1 is 8, then x2 is better, x2 equals 0 is better than x2 equals 1. So the interpretation of which one is better changes when these lines cross. In any case, the interference effect is simply demonstrating that as x2 goes from 0 to 1, the relationship between x1 and y, the slope is smaller, so the relationship was suppressed or interfered with. But the other thing that's happening here is that the slope actually changed from positive to negative. Now that doesn't really have anything to do with an interference effect. It's just what we're noticing here. But it is part of what's going on. And in this particular case, when the slope changes, this is a really, really important case where we want to make sure that we're interpreting properly. So these are called interaction graphs, where you can actually read this graph and look at it and say, okay, well, for this value of x1 and for this value of x2, this is the best case, and for this value of x1 and this value of x2, this is the best case, or the worst case, and interpret these graphs in a way that you couldn't normally. So for instance, if I were to say, what's the relationship between x1 and y, I can't really answer it. It's positive, it's negative, it's strong, it's weaker. That answer isn't appropriate because any answer I give is going to be wrong, because if I say, hey, the relationship between x1 and y is positive, you could say, well, not for x2. And if I say it's negative, you could say, well, not for x2 equals 0. And you'd be right in both cases. So the interpretation of the relationship with a statistically significant interaction depends on the value of that second variable. So I would make my interpretations accordingly. I'd say, if you ask me the relationship between x1 and y, I'd say, well, it's positive for x2 equals 0. It's negative for x2 equals 1. It seems to be moderately strong for x2 equals 0. It seems to be moderately weak for x2 equals 1. And again, I'd have to kind of do multiple interpretations based on the level of the second variable for interpreting my interaction model. And it's important that I do so. It's important that I not skip that step because these interaction graphs are really a very valuable tool in understanding those underlying relationships and making sure that I'm fully describing the complexity of the relationship and not oversimplifying it. For instance, if I had just read the relationship, if we had just averaged all this out, which would be the main effect of x1 in this regression model, I'd have said the relationship was moderately weak and positive, which actually wouldn't be true for my either of these two x2 values. For neither of these would it be moderately weakly positive. It'd be moderate to strong positive or moderate to weak negative. So we want to make sure, again, if we have a statistically significant interaction, we skip over the interpretation of the main effects and we focus on the interpretation of the interaction plots. Now, because the interactions change interpretation so much, we actually have new steps for running the model. So we run the model, we check assumptions just like before, fix them if we need to, recheck. All those assumption steps don't change, but now before interpreting the main effects, we check for an interaction. If the interaction is statistically significant, we look at the interaction plot for the interpretation. If it's not statistically significant, we interpret the main effects just like we normally would. One last thing I'll add on the topic of interactions is that models without interactions assume that the interaction is 0. So let's say I had an interaction and I was feeling lazy and I just didn't want to interpret it. So what I did is I just ran my model without the interaction. Though you can physically do that, it's super problematic because the model without the interaction doesn't actually remove the interaction in the data. It just makes an additional assumption in my model that the interaction term is 0. And that to the degree that that assumption is wrong, that's the degree to which my prediction, my model explanation, and my model overall is going to be incorrect in terms of its interpretation. This would be the assumption in regression without interactions, that one of our assumptions where we say you have all appropriate terms. And if you should have an interaction in there, it's statistically significant, and you don't have it in there, by not having it in there, you're assuming that interaction is 0, and that is a false assumption. So when we talk about checking our assumptions, that's a bad assumption and impacts your interpretation. Well, in this video, we started talking about some of the different topics in multiple linear regression, such as polynomial models and interactions. In the next videos, we'll hit on qualitative predictors and then move into some additional topics in multiple linear regression.